I'll quickly just introduce. Okay, so during the session, and for anyone who's on the live stream as well, you can contribute to the session by going to this website, slido.com, and adding this code ICLR debate, and you can submit a question or upvote a particular comment. And during the session, for the top voted ones, I will sort of read them out to the team here. So today, this sort of session is around the question of structure and learning. And today, the session will be led by Leslie Kaelbling. She, of course, needs no introduction. She's widely known to us, a professor at MIT, has shaped our thinking around reinforcement learning and robotics in many different ways, and has always had this future-looking vision. So when we were planning this session last year, the first thing that Leslie said, I have a great idea, we should talk about structure and learning and the role of priors. And of course, several months later, through bitter lessons and other sweet lessons from the blog posts of Rich Sutton and many others and her own writing, we're here today. And I think that topic of this debate came up in all of the workshops on Monday. So I'm really excited to have this panel. Please join me in welcoming our moderator, Leslie Kaelbling, and our panel, Doina Precup, Jeff Clune, Josh Tenenbaum, and Suchi Saria.
All right, thank you, Shakir. So what we're going to do here, although this is advertised as a debate, our objective actually is to try to arrive at some constructive understanding of the problems that face us in trying to decide how to construct AI systems in a variety of different circumstances. So we don't all agree, that's for sure, but we're also going to try, our objective functions are to be entertaining and to not be unduly polarized or dogmatic. So that's how this is working. We are interested in questions from the audience, and so we encourage you as ideas come to you while we say things that might offend you or excite you or enrage you or whatever, please type in a polite and provocative question and we'll try to get to that. So what we're going to do is just have each of the panelists provide a short position, and then from there we're going to take a conversation and we'll just go where the conversation takes us. And so we'll start first with Doina Precup.
Yeah, so I drew the short straw. I have to go first here. I'm going to argue that a lot of what we need actually can and should be learned from data rather than coming from priors. And this is a position that is, especially in the context of building general purpose AI rather than in the context of applications. So I think when you deal with applications in the medical field or in industry, whatever it is, you need data efficiency, and perhaps this view is not concordant with that. But if you want to build general AI, we would like our systems to learn from data. And over many years, we have tried to build things, and classical AI is one example of that. And we have somewhat failed to do that any better than learning systems could. And to me, perhaps the most powerful example of that is, in fact, AlphaGo, where the initial version of the system used human data in order to gain knowledge and insight, but then the system that ended up being better was the one that learned everything. Now, of course, there are limits to this. There are certain tools that we have learned actually work, certain kinds of neural network architectures, for example, convolutions, gradient descent. So these are also inductive biases that we put in our system, but I would kind of draw the line there. So.
Thanks. OK, next is Josh Tenenbaum.
Hi. So I'm Josh Tenenbaum, and I've been designated to argue maybe the other extreme position, emphasizing the role of priors and what you could build in. Not against learning, but just emphasizing building in relatively more. I'm also, like Doina, interested in general artificial intelligence. But I look at systems like AlphaGo, and as remarkable as they are, and they're remarkable achievements, I'm still struck by how much they don't do, and how much, still looking back on all the successes of the past few years, we still only have, we don't have any true artificial general intelligence. We have a very general toolkit for building very specific kinds of intelligence. AlphaGo just learns to play Go, right? And even if you want to transfer to a different board size, let alone play a slightly different game like chess, you have to retrain from scratch. I think about the human ability, and again, we may have different perspectives on this issue because we have different goals. If I'm interested in the human ability that each and every one of you has to learn so many things for yourselves. And to me, I see the best hope I see for doing that is to take inspiration from how humans learn to be intelligent. So imagine if we could build a machine that grows into intelligence the way a person does, that starts like a baby and learns like a child. It may not be our only route to true forms of AI, but it could be our best bet. I think it is likely to be our best bet, because if you think about it, in the known universe, the only example we have of a system that reliably grows into human-level intelligence, starting from much less, is a human child. And this is a very exciting time to be able to think about AI that learns in something like that way, because we can build on decades of research at this point in the study of cognitive development, using behavior and brain studies, and this is something that I also work on in my role as a cognitive scientist. And we've learned so much. We've learned, maybe a little bit contrary to some of the lessons that some people are drawing, the bitter lessons that some people have been drawing in reinforcement learning. When you look at the science of human learning, we learn a different lesson, that babies' brains actually start off with a lot of built-in structure, and children's learning algorithms are actually much more sophisticated than the kinds of representation learning algorithms that we're all using in our community right now for the most part. Okay? This isn't just about humans. Think about the gazelle that's born on the savannah and within 10 minutes has to be able to learn to walk and even to go over rough ground following its mother, otherwise it's going to be eaten by a lion. Or think about the bird that the first time it jumps or is pushed out of the nest has to be able to fly. The first time. Or birds who just naturally know how to use sticks or twigs or leaves as tools to retrieve food. Now humans, babies, when they're born, they don't start off being able to walk or even to pick things up. But even before they can do those things, before they can walk or pick things up, they already understand the world in terms of some basic common sense concepts, objects and agents, and the intuitive physics and intuitive psychology that goes along with that. That objects interact in some ways by contact and forces, or some simple proto-versions of that. That agents have goals and that they act efficiently to achieve those goals. They also are born with a sense of space and place and some idea of how agents get around in space and place. Okay? And I think at this point, it's an exciting opportunity that we have to be able to build machine learning AI systems that can take those kinds of core systems and learn inside them and within them, and also learn how to revise and rewrite them and go way beyond them. Right? Again, drawing inspiration from humans, we learn so many things that go beyond what we're born with, but that builds on what we're born with. So, and most dramatically and saliently, that's language. The real human singularity in human learning is learning natural language, which builds on those core systems, and then that gives you a very powerful symbolic representational system that allows you to access the full sweep of human knowledge across culture and generations and all of that. So I would like us to think about how we can take the right combination of built-in machinery and powerful kinds of learning algorithms, which include the things we know how to do in neural networks and deep learning and reinforcement learning, but also powerful forms of symbolic abstraction and program induction based on program synthesis. Bring all of those things together to try to build machines that can learn to be intelligent and to really live in a human world so that they can interact productively with us as humans.
Okay, thank you. And now is Jeff Clune.
Thank you. So this debate is usually framed on the one hand or one extreme of human machine learning scientists are going to identify all of the building blocks of AI and then in phase one, and then in phase two, we'll start to put them all together into some giant complex thinking machine. And then on the other extreme, you've got that we're going to learn everything from scratch every time we face a new problem, because that's the best way to go. And what I wanted to take the opportunity today to do is to share that I think that there's a third alternative there that's also very interesting and worthwhile research, and that is into what I call research into AI generating algorithms, or AIGAs. And that is the launching of an outer loop, slow, compute inefficient optimization process, which is searching for and optimizing to produce an AI agent that on the inner loop is actually very, very sample efficient, because the outer loop has imbued it with all of the priors and the sample efficient learning strategies and the building blocks that it needs to be a powerful general AI. And I think that that's kind of a nice marriage of these two extremes, because what it means is that you're not committed to learning everything in the sense of when you have a new problem, you don't start from scratch and learn everything from scratch again, but you can deploy this very sample-efficient AI agent that you've produced via this original process. Now, obviously, we know that that can work. We have an existence proof, which is that on Earth, this happened. So the remarkably unintelligent, sample-inefficient algorithm of Darwinian evolution produced the human brain, which is the best example of intelligence we know about. But I want to be clear that this research direction is not in any way committed to that outer loop algorithm being evolution. There's all sorts of wonderful work that's been done in gradient-based meta-learning, for example, that could get us there. So I think if we want to make progress on this research direction, there are 3 technologies that we need to invest in and research, and I call these the 3 pillars of AI GAs. The first is that we have to meta-learn the architectures. The second is we have to meta-learn the learning algorithms themselves. And the third is that we have to automatically generate effective learning environments so that the algorithm can itself bootstrap from very simple conditions and the production of simple AIs all the way up to producing very powerful, perhaps general AI, and do that all automatically. So I think that there's a clear trend in machine learning that we're all aware of, which is that originally hand-designed systems that work somewhat okay are ultimately surpassed by learned systems once we have sufficient compute. And Rich Sutton and many others have pointed to this trend. And so the AI GA paradigm is an all-in bet on the fact that this trend is going to continue and will ultimately apply to the production of general AI and our most powerful AI itself. So I think that if you believe in this trend, then you should believe that that kind of thinking that we should take a learn-it-all approach should actually apply to the machinery of machine learning itself. So I think that the highest level challenge in this direction is to work on what are the abstractions and what are the efficiencies that allow efficient AI GA algorithms to exist that can run, that don't require all of the compute that was required on Earth, but that can run within the amount of compute that we will have available to us in the coming years. So this is definitely a long-term research agenda, and it's not what I would do if I had to solve a problem in the next 2 or 3 years. But I do think that it may, not necessarily, but it may ultimately be the fastest path to our most ambitious goals as a research community, and therefore it's worthy of our research and investigation.
Thank you. All right, Suchi.
So if I'm going to oversimplify a little bit, I think the previous 3 panelists each proposed a solution path. And what I want to do is to start with some observations and then really leave with questions, because it's not really obvious to me what the right answer is. And I'm also playing the role of the pragmatist here in this panel. So instead of taking extreme positions, I think the answer is going to be, and they're smart. So they didn't mean to, they were given the role of taking extreme positions, but the question is sort of, like the approach we take might very much depend on the goal. So let me start with some observations. So the first observation is the idea that both Josh and Jeff suggested, which is this notion that, if we want to build human-like intelligence, which is, say, an ambitious goal, but maybe I would say even smarter individuals than humans are, we know we can get there using learning, and the proof they gave was evolution. They're saying evolutionarily we got there, so shouldn't we be able to do that? And the question is, evolution is one, very slow, and second, that in the process of getting to us, there were lots of calamities and there were lots of bad and terrible things that happened. So the question is, and I work in safety critical domains, like I work a lot in fields like medicine, where, we don't have the, do we just sort of learn everything and kill people in the process? We may even make humans extinct and then figure out if we can come back to life. So I think a big issue for us, practically speaking, and this isn't just an issue, I think it may just be the showstopper from a learning standpoint, is that, we can't afford to make our civilization go extinct, and we just can't even afford mistakes. Like, small mistakes are big deals for us. So what does it mean for us to think about what should be the right paradigm for coming up with this super intelligent being if we don't want to be slow, because we're all impatient people, and we also can't afford to make a whole ton of mistakes? So that's my first observation and then question. The second observation and then question is sort of, what are the levers we have in machine learning to learn? So the 2 levers that I see are, one, we learn from interacting, right? Like, our machines learn from interacting with the environment. And second, if we can interact, then what do? We learn from looking at past interactions, which is data. So it's a combination of data and interactions. So the question here is, and I don't know the answer, which is, can we conclude that if we had data and interactions alone, we can learn anything we want and we can build any superhuman or super intelligent being? I don't actually know the answer to that, but it's something I want to believe is probably true, but I don't know. And I think the third thing I was going to say is, I think as a field, we focus very hard on thinking about, here's the solution set, how do we make the solution set incrementally better, more efficient, more effective? But I'm actually curious if we have answers to these kinds of questions, which is, what can we learn? What can we learn easily? Like starting from a super intelligent human being that we may have in mind, do we have a taxonomy for understanding what is easy to learn, what's hard to learn, beyond sort of the theory where it stands today? And I think this understanding of what can or can't be learned easily and where the gaps are, and if we can define where the gaps are, it might be easier to try to think about, what strategy we want to take. And I'll stop with the last remark, which is again going back to me being the pragmatist. I think there are so many opportunities where we can accelerate, really make society as a whole better, if we could bring data into play to influence decision-making on a daily basis. And influencing decision-making is all about better use of data to do inference and learning and reasoning and prediction. And those are all areas where machine learning and AI can play a huge role, which means, do we really want to go at evolutionary pace to be able to get those systems? Or do we want to take advantage of all we know to be able to get there? And I think my answer is definitely going to be the latter.
Okay, thank you. So let me just say a little bit, and then we'll let everybody react to each other. I mean, I think one of the things that came out of that conversation, and certainly a view that I have, is that it's really important for us to articulate our objectives, right? And each of us, and each of you, probably has a somewhat different objective. And you have objectives at the big scale and objectives at the small scale. Objectives at the big scale are things like understanding human intelligence, or understanding evolutionary processes, or understanding the mathematics of learning. There's objectives also about making a particular thing work and making it work within a year or 10 years or 100 years. And so I think one thing and one reason that we decided not to make this just like a knockdown debate is that probably none of the answers is true for all the objectives, surely. And so maybe one thing that we could do is, I think maybe, Doina, maybe you could say something about what your objectives are and how it is that your set of assumptions actually is the right one for your objectives, and maybe that's a way that we can continue on.
Yeah, so I have multiple objectives, in fact, and I spend most of my time thinking about how to build general AI agents, so agents that can interact with their environment, like was mentioned, and can gather their own data and can understand the world and become increasingly better at what they do. And in fact, one of the things that we do these days is perhaps not fully aligned with that, in the sense that we often train our agents from scratch every single time, and this has also been mentioned before. That doesn't actually need to be that way, right? We could imagine an agent that just continues learning and growing in an environment and continues improving its abilities and has a way to remember things that it's learned and to bring them back. And I think as a community, we should really focus on that. Right now, we have a reinforcement learning agent. Our impulse is to train it with the whole ConvNet from scratch every single time. But maybe the vision system could be there already, and we could load it up. It's still trained from data when we restart from a good place. So I'm thinking a lot about how do we do a system that can actually grow its capabilities rather than always relearning what it needs to do. So that's what I think about most of the time. This being said, on almost half my time, I also think about applications, including medical applications, and that is a very different space. It's a space where we don't have a lot of data. We cannot intervene because of ethical considerations and all kinds of things like this. And so there, we do put in knowledge, and I find that perfectly acceptable. It's about sample complexity, and it's about getting these algorithms to learn efficiently. But I do feel that as a conceptual thing, we need to think about what are the basic principles of intelligence, and focusing on learning from data can help us get to that. And yes, people are wonderful, but there's also other intelligent systems in nature, and I feel like sort of working on these algorithmic questions will help us also understand intelligence more broadly speaking, perhaps not just people.
So one question, Doina, here is, I think right now we think a lot about let's set up the objective. Once you have the objective and you have the data, you can learn really efficiently. But to me, the bigger challenge, and the keynote speaker right before us challenged us, is half a problem is all our objectives are all broken. And so we set up the wrong objective and then we efficiently optimize. But so the thing is and it's the same thing, right? Like even when we do research, I would say 80% of the battle in doing research is asking the right question. If you don't have the right question, your answers are useless. So I think who's going to define the question? And to me, the question is the equivalent of setting up the right objective. And how do we think about setting up the right objective? What should the right objectives be? And who gets to design that? Until that happens, like a lot of our learning is focused on optimizing post-objective.
Yeah, so that's certainly true. I would say we can have many different objectives, and that's okay. So many of us will pursue different things.
Do you guys want to say something, and then
I can just say very, very, very quickly. I mean, I think, again, we're all pretty broad-minded people here, and but we also have our strong, deep views about things. I love the evolutionary approach. I think when you look at the natural world, to me, it's really just about being science-inspired, right? We look at the learning algorithms that we see in the natural world, and evolution is, as Pedro Domingos has put it, the original master algorithm, the one that really does invent all the other algorithms. Biological learning, the thing that individual organisms do, whether they're humans or birds or gazelles or anything else, to me, it's deeply fascinating. We know that's a real thing that goes on in real brains, and it's remarkable. And then I just point again to cultural evolution, which is sort of yet a third thing, where especially once you have language and other mechanisms of cultural transmission, that opens up whole new possibilities that, I think right now we can say, as much as anything, the success of today's modern AI tools is because of the cultural evolution, the process that goes on in the tech industry and academia, which has huge potential problems. Again, as our last speaker pointed us to, evolutionary processes can take on a mind of their own. But also, like all the things that we're seeing, the power of these techniques have come from that cultural evolutionary process, which is also a kind of learning algorithm that builds the collective knowledge of the community. So I think, I think deeply these are all interesting goals to try to understand from a reverse engineering point of view, and they all have possibilities for building new and interesting kinds of machine intelligence.
Yeah, I would also just add that I think that, like the other speakers, we all probably inside our heads don't just have one thing we're interested in. I think it's all interesting. I'm interested in trying to figure out how to build intelligence piece by piece and put it together, because that teaches me about how intelligence works. But I'm also interested if I can create a process that can automatically create intelligence, because I understand how those kind of processes work, and then I understand maybe the origins of intelligence not only on this planet, but how it might look on other planets. I also think it's fascinating to think about, and this was just alluded to by Doina, is the set or the space of possible intelligences. To some extent, if we're motivated by the thing that works first or the thing that looks like us, then we might have a very narrow understanding of what the total space of general AI might look like. If we could create a process that can generate it and then encourage diverse solutions or just run it many times, we might see the set of possible intelligences out there and then start to be able to abstract general principles about what thinking and sentient life looks like. And so I'm also motivated by very short-term applications. We have the wonderful opportunity as a community to really move the needle and help in a variety of scientific disciplines and important use cases like medicine, and so that's also fascinating. So it's just, what a great opportunity for all of us as a community, because it's all interesting.
Yeah, awesome. So we have some questions from the audience. And I'm going to abuse my privilege here to grab one of them, and I'll read the question and answer a little bit myself, and then we can all react. And then we have this one is from Anonymous. We have some other ones from some people whose names you'll recognize, probably. Maybe you recognize Anonymous. I don't know. Okay, so Anonymous wonders, what kind of result would cause you to change your opinion on how much structure versus learning is necessary? And so the reason I grabbed this question is because I think it's it's a wrong question, right? So how much structure versus learning is necessary? Presumably, you can't answer that question. You shouldn't take the question unless you say, for what? Necessary for what? Necessary to make the thing work tomorrow? Necessary to understand the general principles of understanding? Now, you could, okay, so first of all, I think that question is, as written, maybe not completely sensible. You could then condition it, though. You could say, well, what would it take to change my opinion about how much needs to be built in to solve a particular problem? And that's an interesting question, right? It's very hard to prove a negative. What we're all doing right now, I think, is putting points in a space of possibility. So what we have is a bunch of positive points, pretty much, that say, you can do this way. And we are really, I think, in a kind of methodological crisis a little bit, because we're all putting points in a space. I think maybe enough of us are thinking about what the conclusions are that we can draw from all the points in the space. So let me see what my colleagues have to say about this question. Anybody?
I guess I know one case study that I find interesting, which has to do with intuitive physics, right? So it's an area that we've been working on for a while, and what we mean by that is being able to predict, but also being able to imagine and plan and causally, do all the cognition you need to causally intervene on objects. But it starts with just being able to understand what's likely to happen. Say if this thing hits into that thing, or I have a bunch of balls in a box, or hockey pucks or air hockey pucks on a table or something. This is a place where, over the last few years, there have been a number of people taking different approaches, some which build in almost everything. So in our group, Pete Battaglia and Jess Hamrick, they're now both at DeepMind, building in somewhat less, but importantly, building in some interesting things. But when we were all working together, we built a system that didn't do any learning at all. It just took a game-style physics engine and did some relatively simple approximate probabilistic inference on it to account for a wide range of people's intuitive physics judgments in scenarios of blocks and so on. Okay. And then, other people around the same time, like, for example, a great group at Facebook AI Research, led by Adam Lehrer, Rob Fergus, and others, tried tackling some of the same problems, but just in basically an end-to-end image-based approach. They didn't build in any physics or any knowledge of objects at all. And their system worked in some impressive ways. And most impressive, they could get some nice sim-to-real transfer. But it still required a huge amount of training data, and at least it didn't seem to generalize very far beyond the few blocks scenarios that had been trained on. And in the meantime, a number of people, both in industry and academia, have been trying different kinds of systems. And what I think the general view, we've had a couple of workshops at NeurIPS on intuitive physics, and I think there's sort of fairly broad agreement, is that it seems it's not about an argument for necessity, but it's an empirical result that the community has converged on, that building in some aspects of the physical world, such as the idea that there are objects, discrete objects, and that they might interact through something kind of like forces or pairwise interactions that maybe depend on a spatial neighborhood or even the notion of contact. That, for example, if you build some of that in, which are some of the key ideas in, say, game physics engines, but not all of them by any means, but if you build machinery that can naturally exploit that, like various kinds of graph-based networks, like interaction networks or neural physics engines and so on, those are, we can't prove that those are necessary, but they're massively valuable in terms of like data complexity and the ability to generalize. So I think it's just a nice case study for the community. It doesn't necessarily change any one person's minds or prove something necessary, but it's a place where we've learned some empirical lessons that building in certain kinds of basic inductive biases about the nature of the physical world that not only do we learn but evolve in, that actually those turn out to be very valuable.
So it can be very valuable to build these things, and I'm still not convinced that they can't be learned from data. And so, in particular, right now, a lot of the complaint is about sample complexity. How many examples do we need in order to train these systems? And generalization as well. And my sense, and I think it's shared by other people in the field, both at DeepMind as well as at Mila, is that if we had the right kind of approach for the learning algorithm, it could learn these things. So, typical example is causality, right? Causality is just very important. If we got that right, if our models were able to be not predictive models, but causal models, then perhaps we would be much more data efficient and much more computation efficient, and we wouldn't need to build this thing in because the model would learn about objects and things like this. So that's one.
About building in the notion of causality?
No, having models that are structured so that they can essentially understand and learn about causality rather than just learning about prediction. So I think that's one thing. I want to say another thing, one short thing about methodology, since Leslie mentioned that, because that's something that I feel is also very important for us as a field. And it's been wonderful seeing all the great work at the conference, and it's been wonderful seeing all the great improvements that people are making on various metrics concerning these learning systems, accuracy and return, and all these kinds of things. But it's I think also difficult to make progress when we care a lot about the numbers without also understanding a little bit more about what our systems do. And so, yes, it's great to have a reinforcement learning algorithm that gets better return than some other reinforcement learning algorithm. I'm all in favor of that. But unless we also understand why and under what circumstances there is limited utility to this particular result, and it will perish in the next 2 months when the NIB submissions come out, and somebody else will have even better returns. So I would really like to argue that we need to probe our systems, not just look at their behavior qualitatively, not just measure them quantitatively, but to design probes that try to test particular hypotheses about our systems, right? Maybe our systems already learn, for example, that they live in 3D space. Maybe they learn about objects. We just don't know that they know that. And so sort of designing our experiments in a way that kind of probes that behavior seems to me to be important.
Yeah, so I think I'm in line with Doina here, and I just wanted to ask Josh your opinion on, by analogy, I agree that it might give us a lift to build in, whatever we think is helpful, like a notion of objects and causality and things like that. But how do you see the analogy with, say, Huygens SIFT, which at the time looked like the right way to do it, and we're going to build on some structure of the world, and we're not going to have to learn that, and that's going to give us a big lift. But it's not ultimately, as Doina was suggesting, that we can learn those features, but ultimately that the learned features end up performing much better. So I just wonder how you think about all the claims that we should build in X. I see analogously that eventually they will be learned, and then probably the learned solution will be better than our attempt to build in X. So it's not that we don't need X, it's just a question of, well, what's the best way to get X?
Yeah, I mean, I think that the Huygens SIFT and then sort of deep network features lesson is a very instructive one. And again, we see things in the intuitive physics area, perhaps a similar story is unfolding, but we're just still in the middle of it, right? So right now we're at the stage where, I think, like from an AI point of view, the best kind of models we have, generative models of the physical world, are physics engines, right? Ones that have been built by humans for playing video games. You can run them super fast, and they can couple them to a graphics pipeline much faster than real time. Okay. At the same time, we know there's a lot of things they don't capture. And people are in the process of trying to build kind of learnable physics engines, which take some of the aspects of physics engines and strip out some of the parts and try to learn the rest. And it's not clear where the data comes from exactly, and what the right learning algorithms are going to be. But it might be, and some of the people, like for example, the guy who wrote Bullet and PyBullet, right? He's actually working on this. Some of the best game engine engineers are engaged in that process, just like many of us in AI. Now, we don't know where that story is going to end. If we look at the story of visual feature representations that don't just include Huygens SIFT and all the current deep convolutional networks, but all the work that people have done in image processing, you see again the community over a few generations of research, has kind of converged on certain ideas like hierarchy and kinds of linear filters with then certain kinds of key nonlinearities, and then repeated in those motifs, right, in layers. Whether you call it a neural network or whether you call it some other kind of, a texture of textures, like I'm thinking of Jeremy Debinet and Paul Viola's lovely work about 20 years ago. There's many ideas, or many versions of that same kind of idea. Huygens SIFT for one moment where people thought, oh, this is cool, we made some progress, right? AlexNet was another huge moment, right? And so when we look back on the history of, say, intuitive physics, whenever we get to a similar point of maturity, we'll probably see similar interesting points that I think, again, like in the image representation community, are going to really reflect the combination of key architectural motifs, which were discovered by cultural evolution, not by learning algorithms, along with certain kinds of basic sort of learnable machinery inside those architectures.
Josh, I have a question for you. So is the reason you think we need more than just learning here because you want to, like, you're not actually believing that the physics engine couldn't just be learned from scratch, right? Like, you could effectively just interact with the environment and learn it. Is that correct? In other words, are you saying that, yes, it's how, can we just learn the entire, can we learn physics by just interacting with the environment, observing?
Well, I think in an evolutionary sense, that's exactly what happened on the planet Earth.
Yeah.
And, you know, I'm very interested in Jeff's idea that we could recapitulate some of that in AI, and hopefully it won't take a planet-sized computer. But I think, you know, we have to be worried about that as a risk also. Like, I mean, you know, again, OpenAI has made some of their calculations public. You know, they're one of the biggest organizations really trying to do that, and talking about, you know, simulating evolution. I guess you guys are doing some of that. DeepMind, of course, also. And the compute is huge, and we're still just barely starting to even start to make progress. So if you extrapolate, it's not at all clear that the current route, and I mean everything, including the whole complete software-hardware stack of modern deep reinforcement learning, is going to be able to, is going to really deliver on that evolutionary promise of just pure learn a real physical model from just interacting with the experience. But the fact that human children need much less energy and much less time is proof that there is another possible way.
Yeah. Can I just quickly comment?
Yeah.
Yeah, so I think it's a fascinating, open, uncertain question as to which path could get there the fastest or will get there the fastest. So I think the manual AI path is intrinsically worthwhile, and it will eventually, we'll figure it out. And I think the AI GA route will eventually get there, and it's also intrinsically worthwhile. I think if we had like infinite compute today, the AI GA strategy would be the fastest path and would get there. But it takes a lot of computation, and we're going to need to invent a lot of abstractions to make it work very fast. And so I think it's an open question whether or not the manual path will get there before we have the sufficient compute and the sufficient algorithmic abstractions to get there. Eventually, I think there'll be a crossover point where AI GAs will outcompete the manual path, but the manual path might get there before we have sufficient compute for that to happen.
Except, Jeff, I think you missed this fact that, like, don't we want to not kill people along the way? Like, your assumption is it's completely fine. We have infinite compute, and then we'll just get there. But what about all the things, bad things that could happen?
So I think that's a fascinating question, and I think it's a really, really important question. And if I was given the ability to like give the full version of my pitch for this idea, I definitely would have had a section. In fact, I'm writing something right now that I'm going to post to archive soon. It has a whole section on the ethical considerations of this idea. And to be clear, it's not even, there's the general question about should we be creating general AI at all, and all of us, I think, should wrestle with that question, and we have to discuss it and debate it. But I also think there are some unique ethical considerations that come from this particular strategy of trying to go for AI. Because obviously, if you're creating an AI GA, you have far less control. You don't know whether or not it's going to be value aligned to humanity. You're intentionally trying to create a runaway process. So someday you might suddenly get the ingredients correct, and then voila, you go to sleep and you wake up, and something magical has happened. So it looks very different in a lot of ways. So I don't in any way want to downplay those considerations. They're very real. But I think if we're just having a conversation about, that starts with the assumption that we're trying to produce general AI, and then what's the fastest way to get there, then you get all the arguments I've given so far. If we want to have a separate conversation about the ethical implications, whether I think we should and we need to, then we should get into the large question of which we should make it, and the unique pros and cons for each of the different methods of getting there vis-a-vis ethics and safety.
Okay, good. I'm going to stick in a last word on that debate and then open a new question. So I think one thing that Jeff didn't mention too much maybe was the physical infrastructure required potentially to do the evolutionary approach. So you talked about compute scaling up. But if I want to make robots, and you've made robots, well, then they need to interact with the world unless we can make a perfect simulator. And if we have to make the perfect simulator, now we're relying on humans again in a way that perhaps we shouldn't. So I'm not sure that we can get that taking off that maybe you suggest. But okay, so good. So I'm just going to stop with that, and we'll see. Okay, Jan, who's there? Oh, there he looks. Okay, good. So Jan, he says, I can tell who he's talking to by the tone of voice here. Symbol manipulation has no place in deep learning. Change my mind. Okay. Oh, no, I'm going to go first. Okay. So I don't. Maybe this is not a good thing to debate because I think symbol means something different to everybody. I would argue that people who are finding embeddings of complicated states and then doing computation using the lower dimensional embeddings are already doing something that looks a lot like symbol manipulation. So maybe you've been doing it and you don't actually know. Okay, Josh.
Well, We'll check Twitter afterwards, but it's certainly not my place to define what deep learning is. I think one of the reasons why deep learning is an interesting concept and movement is because different people can define it in different ways. But I'd like a version of deep learning where symbol manipulation not only could have a place, but already has a place. So for example, there's going to be a talk tomorrow by Joyan Mao over there, not to point, on the neural symbolic concept learner, which is one, I think, very small step, but a kind of intriguing idea about how to combine some deep learning motifs with some cognitive science abstractions about symbolic concepts and use those to build systems that do somewhat more data efficient and generalizable, so for example, visual question answering. But there's a whole community of people who are trying to find, or who are trying to explore interesting ways for symbols to live inside systems that do some kind of deep representation learning. And what I mean is that they learn multiple layers of concepts and abstractions that build on each other progressively. I think that's a version of deep learning that doesn't commit to vector space representations, but that can include vectors, symbols, and various interesting combinations of those. And I think increasingly we're going to see systems like that outperform what you could do with pure vectors or symbols on their own.
So, but do symbols need to be there from the beginning? Because what this sounds to me like is actually that we want systems that are somehow compositional and where we can take parts of the system and make new stuff out of that. But it could be learned. It could be that the system learns to represent symbols and then learns to manipulate those symbols. And there are several posters, I think, today that we're looking at this kind of
architecture. No, I mean, I think, again, there are there's many different versions of what it would mean for symbols to be in there to start off with. But certainly something like having basic capacities for compositionality, for composing structures together to get function and what becomes meaning that wasn't there from the beginning, that is something that I think you're going to have to build in. And that is something that isn't just built into many generic neural network architectures.
Meaning as in people assigned meaning, or meaning as in the system knows what it means for itself?
Whatever you mean. But I do think, while I have the microphone and then I will give it up, I do think it goes back to some of the things that you guys were both talking about, that if you want to build systems that I think can interact safely with humans, that we can understand, that we can find, that we can see meaning in, and kind of believe and trust that things mean the same thing as we hope we do when we interact with other humans. That's a reason to try to build this kind of AI as opposed to evolve some other, what might turn out to be very alien and uncontrollable kind of AI.
Just as a very short comment, I sometimes think we all mean the same thing, but then I talk to my kids and I'm not so sure about that.
Cool. Okay, so here's a question from Joshua, who I saw there back here. Oh, there he is. Okay, good. So he says, we of course need priors, but to obtain the most general AI, so that's an objective function, to obtain the most general AI, we'd like the least amount of priors, which bias the most towards AI tasks, don't we? Okay, so
Yes.
Also, yes.
I feel like it's a very non-controversial. Okay, so actually, I have an audience question. More like I want a yes/no, and will you allow that, Leslie?
Sure.
Can I ask?
We can have what, 1 hand, 2 hands, or we can just.
Everybody can have, raise your hand. It's yay/nay question. Okay. So first question is, everything can be learned, yes or no? So raise your hand if it's a yes. Anything and everything can be learned. Okay, so actually flip it. So you mean you disagree, can you raise your hand? Not everything can be learned. Wow, that's cool. Okay, so one thing that would be really cool is, if Leslie will allow in this time during this debate, would be to at some point come up and say what you think can't be learned. Because I think that would be actually interesting to hear.
Yeah, you can type it into the thing and Shakir will find
The
Yeah. Yeah, okay. If you think something that you think can't be learned, type it in and we'll talk about it. Well, okay, so the least amount of priors that bias the most toward AI. Yeah, I mean, I think presumably, well, I don't know about that. I mean, I guess the question is, does the system that we end up with do the job we wanted it to do, right? That is the thing that we have to do. We have to write down our objective. We could say, we want a system to be interpretable. We could say we want our system to work in a really broad variety of domains. We can say a bunch of things like this. My own view is that once you have specified the problem that the agent is supposed to solve, I guess I'm agreeing with Jeff, actually, which is kind of strange. Once you specify the problem the agent's supposed to be solved, then there's only one answer for what program that agent should be running. Now, our hard problem is to find that program, and I guess maybe I think that's what we're arguing about. And then there's the question about whether human engineers will be able to help that process along, or whether they're just an impediment to the evolutionary strategy.
Just because I just want to say one thing in response to Leslie and Jeff, which is you referred to it as the manual approach, and you talked about human engineers. And I think human engineering and ingenuity is great. But I just want to say the way I would prefer to call it is the science-based approach. I'm not arguing that every intuition that even a very smart human being thinks is the right way to build something is the right way to go. But I'm saying the community of engineers, I think, is going to be, at least for the approach I'm arguing, at its most successful when it is working together with the community of scientists who have been studying neuroscience and cognitive science, the structure of brains, and the actual algorithms that build a mind as a child develops, for example. Or if we're talking about evolution, then we should be talking to evolutionary biologists and computational people who have who've explored that from a computational point of view, and so on. And I think if we build the tools, the frameworks, and again the community that allows engineers to draw on those insights, to challenge them, and together, I think it's not like any one scientific community has figured everything out. Far from it, especially in cognitive development. We only have hints of the full picture, but that's a very virtuous cycle that we can get into as a research community.
So I agree that there is tons of science to be done in what I'm calling the manual approach, but I would just say that they're different scientific quests and they're different scientific disciplines. So in what I'm calling the manual approach, there is the science of identifying each of the building blocks that will go into the machine and the right variant of that building block and how we need to put them together and where we need to sprinkle in machine learning to get it all to work. And that is a very, very huge and difficult grand challenge of computer science. And I think that the scientific questions are also present, but different for an approach that was trying to create an AIGA. So instead of trying to say, discover attention mechanisms or batch norm or convolution, you'd be saying, what are the scientific basic ingredients that need to be present to kick off a process that will discover things like convolution and attention mechanisms and batch norm or whatever is required ultimately to be there. And so there's a different set of hypothesis testing and there's a different set of building blocks. It's not a building block free approach, and this is what I think Joshua was alluding to. We need to discover the simplest set of building blocks that might kick off that process if you're committed to the AIGA approach and do that science, or if you're committed to the manual approach, which is also intrinsically worthwhile and want to do it no matter which one is the fastest path or the most effective path, then you have to do a different set of science and conduct a different set of hypotheses. So I resist only one of them having the word science.
I wasn't saying only one.
Yeah. So I think there's a lot of great science to do on both.
So I feel like Jeff is really mischaracterizing the manual thing in the sense that he's making obviously the other one look much better and the manual thing sounds stupid. So,
I'm trying to do that.
But you're doing that. So let me explain what I mean by that, which is obviously the point isn't like let's figure out what the building blocks are and then the only thing we learn is how to piece together, which sounds very minimal to me. I think in reality, I think most of us will agree, the issue is you have practical constraints, right? You want to be safe. You have limited data, so you can only take advantage of that data. There's only so much you can sometimes, what Doina said, if you're solving problems where there's confounding, the data can't tell you, you need extra knowledge that comes in the form of domain expertise or something external that you'll have to bring in. So the real challenge is always sort of more a notion of, starting from how fast do we need to solve this problem? How accurate do we need to be? How much, what are our constraints in terms of safety and exploration? And then figuring out what's the most, whatever we know, and then starting from whatever we know and learn everything else, right? Which to me is I want to call that the intelligent other solution. So it's like the Jeff solution and the manual, I'm calling it the intelligent mixed hybrid approach. Are you going to disagree with me now?
I just want to be really clear that I'm not trying to in any way be pejorative. I think both paths are independently worthwhile. And
I was being provocative.
Yeah, sure.
On purpose.
We finally got to sparks in the debate, so that's good, entertaining. I think they're both independently worthwhile, and I think a way that you can conclude this is just imagine the thought experiment. You know, if one path won, we'd still want to do the other path, and vice versa. And certainly, if you wanted to build a particular thing, and you wanted to have interpretability, and you wanted to have safety guarantees, and you wanted to build it soon, then you would take this kind of engineering approach. But I don't mean that there's nothing wrong with an engineering approach. I mean, engineering is wonderful. It builds the International Space Station, and it built, you know, the jets that fly us between continents. And there's a lot of hard science and engineering that goes into it, and it's a great discipline. So I don't, by calling something manual and engineering, I don't mean to put it down. I just mean to be very clear that this is kind of the path that we are on implicitly. And it involves this kind of a commitment to first identifying the building blocks of intelligence, and then at some point taking on the Herculean task of putting them together. And so I think it's good to kind of stare in the mirror and see that this is what we're kind of implicitly, most of the people in this room are committed to. And I also think it's fun because once you do that, then you can see that there is another approach that's worthwhile and worth considering. And I think they're both worthwhile.
Cool. All right. I want to issue a challenge maybe to the people here. So I think if we didn't believe in some amount of building in prior information, we would not be presenting the papers that we're presenting at this conference. We would be enumerating programs in the order of complexity and seeing if they worked, right? So everybody who's here with the paper has designed an algorithm or a network structure or something, right? And you're proud of it, and it's awesome, and it works, and it solves problems. But it's not nothing, right? It's emphatically not nothing, or we wouldn't have anything to talk about. So I guess I would encourage people to try to be really revelatory about the assumptions. And in any given paper, there will have been some things, some assumptions you've made, or positions you've taken, or algorithms you've built in because you think that they're necessary to this thing you're doing. And some of them are peripheral, right? Because we all have to put in peripheral things too. So I think it's a really interesting and important maybe for everyone to try to say, what is it that they're contributing? What's the new idea? And how is it actually a piece of structure that will contribute to some bigger approach?
That sounds like a great idea.
Ooh, okay.
Do you want us to react to that? Okay, so...
What have you built in? Okay, so here's a question for Doina. What did you build in last week?
So I can tell you something that I can really believe in building in. One is interaction with an environment. I really believe that interaction is crucial, and that systems that just watch are severely limited in their ability to learn. So that's obviously why I work in reinforcement learning, because we build systems that interact with their environment and can learn from that interaction. I also believe that compositionality is important, and that if we can get our systems to build small pieces and put them together in different ways, that there's just a lot of richness that can come out of that. So that's one reason why I work in temporal abstraction, because we can build these primitives and then put them together. So those are my two main things.
Actually, can I ask a question to what do you think? So I feel like compositionality is something we've been talking about for 30 years at least in AI, and we've been talking about learning from interaction for at least 30 years, and we've been talking about learning from data and learning from interaction and mixing it. What do you think are our blind spots? What do we not know? What do we not understand? Like, what part of it do you think is really controversial in terms of, like, our current thinking? Approaches we're abandoning that we shouldn't, aspects of learning that we're ignoring, that maybe we need to step up our game as a community?
So I think that's very hard to tell, right? Because if we knew it, then we would go there. So it's kind of an impossible question to answer. But there's certainly aspects of what we do that are less looked at. Right.
Doina, the perfect opportunity to talk about work so that people can follow your work and cite it. I'm giving it to you.
Well, really my goal is actually to learn these abstractions that can be put together in complicated ways. And there is one very big open question that I actually don't know how to solve, which is exactly what should be the objective of these building blocks, right? And I don't know, maybe Jeff's algorithm will figure that out for me. What should be the objective function? I don't know.
So I also believe that the best learning algorithms don't require a lot of injected domain knowledge, but they should also take advantage of domain knowledge if you give to them and do much better, because you're giving them a huge head start, and that should save you a tremendous amount of computation, at least in the short run. And so I frequently am doing the kind of papers that Leslie is mentioning that is very much in the what I'm calling the manual engineering approach to AI, which is trying to build it piece by piece and inject domain knowledge. We had the Go Explorer algorithm, and we definitely took advantage of domain knowledge to try to move the needle on Montezuma's Revenge and hard exploration domains. And if you looked at my history, you'll see tons of that work as well. So I think that's very important, and we want to be taking advantage of that, and it's an important research direction.
Okay, so we just got an infusion of interesting things that I can't quite synthesize into something coherent. But let me make a list of things that the audience thinks can't be learned, because it's pretty interesting. And it's, I guess, suppose a direct challenge to the evolutionary view if you take evolution as a learning process.
It's not an evolutionary view.
Okay, good. The long time scale meta learning view.
AIGA.
Okay, good. So here are things that the audience, that some audience members believe can't be learned. Random number generators, that's kind of fun. Causality, consciousness, a halting predicate for Turing machines, and the probabilities. Okay, some hairy math stuff. Empathy can't be learned. I mean, I would argue with that one, right? I'm empathetic with you, not because I actually like you, but just because we work together as a society better that way. I don't know. Love, non-computable functions, halting problem, I don't know. Can these things be learned?
I don't understand, because we have the existence proof for all of except the RNG case that they exist in us, so that they have been learned. Like evolution produced you, and you have empathy, maybe everyone except Leslie.
So you're saying if you consider evolution as a learning algorithm, then I think it's pretty clear that all the phenomena of human intelligence, or any kind of phenomena of intelligence that we know, can be learned, because evolution learned it. The question is whether any of the algorithms that we have right now that most of us consider tractable or even remotely accessible with the resources we have, whether they could be learned that way. I think that's really the question.
I agree, and right now is very different from, in principle, give us a couple decades or a couple centuries. I think it would be really interesting if for some reason you thought that love, in principle, can't be learned within a reasonable amount of computation. So you have to believe that the amount of computation that we had on Earth is so many orders of magnitude larger that can learn love, but we can never come up with an abstraction or an efficient algorithm that can get us to something that can love or feel empathy. And I feel like that's a very, very strong hubristic position to take. Like, how could we possibly know that it's impossible to do what has already been done?
So I find it difficult to think about, how would we recognize that an AI system actually has love for something or someone? I mean, it's just hard to recognize it in people sometimes, too. How do you recognize it? Well, you recognize it because they do certain things, right? They might be nice to you, and they might be willing to self-sacrifice, right? Or to spend time doing things like chores and stuff like that. So it's hard to define these things, and I feel like sometimes we project a lot of our sort of human understanding onto AI systems in an unfair way, right? So if you took one of the members of the audience and you stuck them in an MRI scanner, and you made them think about various things, certain connections would light up in their brain, and their neurons would be firing, and you're looking through the MRI, and you're asking, are they in love, are they empathetic, and so on. There's a wide gap in between those two things. And right now we are at this level of analyzing our systems that is more like the MRI scanner. We look at the neurons and we say, oh, no, this one's firing, that one's not firing, and maybe the system doesn't know love at all. But maybe if it were put in a safety-critical situation, it would actually self-sacrifice. So I really think that we need to bridge this gap between the kind of analysis that we have now, the kinds of things that we understand now, and where we really want to be later.
Suchi, do you have anything to say?
So I think of the examples that were given, even including causality, if you can interact with the environment, you can learn it. And I think what Josh said, which is our existence proof today, everything we've gotten to today, if you consider evolution to be learning, then we are basically here today. So I'm still actually really intrigued by the question, which is there something that we believe can't be learned? I haven't been able to come up with a good answer, but I am actually curious. So that's one question. And then the second, which is really for the community, so it'd be really interesting if anybody believes otherwise to write something on it. And then the second question here is like, given that even if we believe everything can be learned in some super long time scale using infinite compute, maybe that's not even the problem we should be talking about. A community really needs to be talking about how do we accelerate, finite horizon learning under constraints. And, that's really maybe what the field should be thinking hard about, and how do we figure out what to take advantage of, how to take advantage of it, and do it in a safe way.
Okay, one quick comment from Josh, and then I'm going to finish this up.
Yeah, I think this is trying to respond to what you were saying, which is not necessarily something that is a blind spot, but it's just an area which some people are starting to work on and could benefit from a lot more work on, right? Which is pretty much all the learning algorithms we have are some kind of search, right? Gradient descent is one kind of search. There's various ways in which stochastic gradient descent we think is more, searches for and finds more efficiently and more robustly, let's say in certain cases, good local optimum. I think the view that I'm talking about, and this goes back to symbols and what's the place of symbols in AI, not just deep learning or compositionality, is one which says really all of our knowledge is code of some form, right? And code, computer code, programs, right? And in some sense, another universal view of learning besides the evolutionary one is the idea that learning is programming, right? Whether it's evolution writing the code of DNA and the programming machinery that makes that work, or we sometimes in our research we've started to talk about the child as coder or the child as hacker, that children's learning can be seen as like writing programs or even writing whole new programming languages. Okay, so that remains a very, very hard problem because for the most part, we don't know how to turn the really interesting hard problems of coding into something with a smooth optimization landscape where the mechanisms of, say, gradient descent work so well, right? So how do we solve hard search problems in, say, for example, the space of programs or whole programming languages, and do that anywhere as efficiently as biology, whether it's evolution or children's minds are able to solve that problem? If we can make progress on that, I think that will be one of the key linchpins for making a lot of the different visions we have all come to fruition.
Okay, so I would like to end by exhorting everyone to state their objective function clearly. And when you write a paper, say what you're building in. And if the answer is nothing, then ask yourself if it's really nothing. It's okay if it's okay if you're building something in, but say why and say what it is. And so with that, I would like to thank my fellow panelists and Shakir and all of you for your questions.
Thanks.